Hello everyone. My name is Kunli Ma. I'm a senior student here at Udall Medicine, majoring in a map, and I plan to graduate this semester if I if I can successfully survive all the humanity and ethnic and communication B courses, and do not get a probation from school because I did not attend the COVID test twice a week regularly, like what the university required me to do. Okay, so today our topic is anisotropic microswimmers in surface gravity flows and surface gravity waves. This is a project that I've been working with Professor Tifo and Professor Pajara for 8 months. Okay, let's get started. So introduction of the problem that the swimmer we deal with in this problem are spheroids, which has a shape parameter of eccentricity of lambda, and this lambda is between -1 and 1. So if you can see that I have some notes here. It's because it's actually my third time of recording this, and I also mess up my Windows recording software. Okay, so let's keep going. Lambda will be between -1 and 1, and for lambda equal to 0, it's a perfect sphere. And for positive lambda, then it's a prolate sphere. It's like a football, And for oblate microswimmers, it will have a negative lambda and swim in its large surface direction. Okay, and these microswimmers can only swim in its axial direction, which means that the sphere is symmetric, so we cannot determine that which direction is swimming. Okay, but for this prolate microswimmer, it can only swim in its long axis. In this direction only, and for oblate, it can only swim in this direction. Okay. And the basic model behind it. Okay, so the velocity field, the fluid field that we deal with is called the surface wave under gravity, and we make some approximation using the deep water approximations. And the original equation have some cosh and sinh in the expression, and we can simplify those a lot using these deep water approximation, because if you imagine that for an ocean like this, okay, the wave oscillation at the top is relatively small compared to the depth of the water tank or the river bed or ocean. Okay, so the eta here is actually the horizontal position z, and a here is the wave amplitude, and k will be the wave number, and omega is the wave frequency, and ux is the fluid speed, the fluid velocity in x direction, the x component of the fluid velocity, and z is the z component. Okay, and this is the Jeffreys equations, which is how these spheroids microswimmers being affected in a viscous fluid. Okay, and P here is the orientation of the microswimmer. For this question, we have a specialized coordinate system for this microswimmer. Okay, so if the microswimmer swim in this direction, then we have a p vector of 0, 0, 1, 0, 0, 1, because it's pointing up. is pointing up, and there's no y component, there's no x component, and there's only z component. It has to be normalized, so it's 0, 0, 1. Okay, so it's just like so p here is actually a position, not position, the orientation vector. Okay, and we define the angle from here to here. So we say that this is phi equals to 0, and it's oriented in like this. The swimmer will orient like this, and if we rotate this 90 degrees, and then it becomes phi equals to pi over 2. Okay, and here the omega is called the local rotation rate tensor, which is 1/2 of the grad u times minus grad u transpose, and this s will be the string rate tensor, which equals to 1/2 of grad u plus grad u transpose. Okay. And this Vs will be the swimming velocity. Okay. And because the p here is it's an orientation vector, we can decompose the equation into 3 directions. Okay. So we use the velocity field here to calculate these two tensors and plug them into the equation, into this equation. Okay, and we will get these three expressions. We observe that for this 3b, which deals the y component of the direction. If we start at py equals to 0, then it will stay in this direction forever, which means that if we assume there's no motion in the y direction, then there's no y direction anymore. Okay, actually later on we realized that this py equals to 0 is actually stable, which means that wherever whichever orientation in py you start with, you will finally fall back to py equals to 0 at the end. It may just take a lot of time. Okay. So based on our definition, then we have px equal to sine phi and pz equals to cosine phi, because we want to do this substitution so that we can decrease the number of unknowns. Okay. So because we define the angle phi in this direction, so this is angle phi. If this is angle phi from 0, okay, and this component will be sine phi instead of cosine phi. Okay, so px will be sine phi and pz will be cosine phi. Okay, and inserting the expression and non-dimensionalize it, at the end we will get a dynamic system with 3 dependent variables like this. Okay, and this is the dynamic system that we are going to analyze for the problem. Okay, so yeah, let's take a look how the microswimmer moves in general. Okay, so ignore the black lines. Ignore the black lines for now. Okay. This red curve, for example, let's look into this red curve here. Okay, so the microswimmer oscillates, and at the same time it moves forward it's a little bit similar to the Stokes drift, where the swimmer will move something like this. But since we have a swimming velocity here, we will also have a overall motion of the particle. It's swimming, and this swimmer will finally swims down to the bottom of the water, and for this one it will swim back to the surface. Okay, so actually I have more graphs to show you. Okay, yeah. So actually these lines are not straight, are not smooth smooth lines. These trajectories are actually oscillates. For example, this blue one, okay, it's oscillates all the way, and then end up at the bottom, and this blue one is oscillates, and at the end it can come back to the surface. And because we actually don't know what will happen if the microswimmer swim back to the surface, we usually just assume that it will stick with the surface and move with the surface together. Okay, so the interesting that I found is that if say that these three swimmers, this blue, red, and yellow swimmer, they all start at a certain depth. For example, minus 0.1. Okay, and then I vary the initial orientation of the microswimmer, and sometimes it can swim back to surface, and sometimes it cannot swim back to surface. So there's a separatrix of it. So like there should be a critical angle. There should be a critical angle. Affecting this behavior. Okay, we can see that here I actually adjust the angle very carefully. You can see that there's only 0.01 difference in degree. Okay, and that small difference can decide whether this swimmer come back to the surface or not. Okay, so in this diagram, this blue curve come back to the surface really fast. It doesn't go to somewhere that is very deep. But actually, that after I run many simulations, it turns out that this microswimmer can actually reach to somewhere that is very deep, and still manage to come back to the surface. And our first goal is to understand this, like find that critical angle, reach depth, because ideally that if say that the swimmer start at this depth, okay, and how do we know whether it will go back to the surface or not? It shall depends on the orientation, right, which is phi. Okay, so there should be maybe one or maybe two, but we don't know. Okay, we don't know how many critical orientations are there. Okay, so actually at the early stage that we fall into a pitfall of finding fixed points, but that doesn't turns out to work well. Okay, and then we notice that, well, there are oscillations and also a translation moving in the long run. Okay, so we try to expand this into two time scale, and here is how we did it. So we rewrite the solution vector x, z, phi in terms of two time scales. Okay, and so the fast time scale is lowercase t, and the lower time scale is the t equals to epsilon squared times lowercase t. Okay, And since alpha and then nu are small, we express them in terms of a small parameter, as alpha goes to epsilon alpha and nu goes to epsilon square nu. Okay, and in the simulations then we use alpha equals to 0.1, etc., etc. Okay, and this is kind of a common this is a common parameter that we use in this kind of environmental process. Okay, and then we get this this two-time expansion of the ODE system. Okay, and then as we usually do, we analyze it at different order of epsilon. So at order of epsilon 0, it's simply this. Okay, which indicates that the leading order quantities are only a function of the slow time t, and at order 1 we have this, and we can actually solve this. To have expression for x1, z1, v1, and remember that x is equal to x0 plus epsilon x1 plus epsilon square x2, something like that. Okay. Yeah, and then we proceed on at order of epsilon square. Then here actually we have a non-trivial solvability condition obtained by averaging equation 11 over a period. So we actually have to insert the expression here. For example, z1 equals to alpha times e to the z and times cosine x minus t. We insert those here. We insert those expression here, and average this over a period of 2 pi. And then we can find that the delta t, not delta t, dx dt will be nu sine phi plus alpha square e to the 2z. Okay, so this is supposed to be the average system, or the slow time scale motion. Okay. Yeah, and we can also, of course, we can proceed on to find the next order solution, x2, z2, and v2. And this is not very useful for now, but it's actually very useful later. Okay. So the average system, yeah, let's see some trajectory of this slow time scale motion. Okay, so if we observe 15a and 15b and 15c, we can see that the x doesn't show up at all on the right hand side. There's no x here. There's no x here at all. Okay, which means that 15a can be decoupled from 15b and 15c, which means that this two can form its own dynamic system, and therefore we can draw a physi plane that we can analyze whether the microswimmer swims back to the surface or not. Okay, so here is is two phase portraits for this decoupled system, z-phi plane. Okay, so this graph we use lowercase lambda equals to plus positive 0.6, so it's like it's of aspect ratio of 2, and this field looks like a football moving in this direction. And for this we have a lambda of minus 0.6, and this is like a disc, not a bomb, not a bomb, a mantle sugar moving this direction. Okay, and this has aspect ratio of 1/2 of 1/2. Okay, we can see that the plot, the trajectory is actually symmetric with respect to pi over 2 and 3 pi over 2. So pi over 2 is this direction, is this orientation, it's swimming to the right, okay? And this will be swimming to the left. So this is a polar version of the graph. So at the origin, it's the deepest location of the water tank or the environment, okay? And the outer bound will be the water surface. So if a swimmer starts at this, will swim all the way down to the bottom of the water, okay? And if the swimmer start here, will swim all the way down a little bit, and then swim back to the surface. Okay? And the shaded, the gray area here means that all the swimmers here in the middle will end up at the bottom. Okay? So, yeah, so after we find this averaged system that we want to predict the whether our average system predict the effect accurately, okay? And then at the beginning that we think it works pretty well, but afterwards then we find that our average system will deviate a lot if the swimmer like moves for a long time. For example, the average system is supposed to track this blue line very well, right? Track this blue line very well, but in fact it doesn't. In the beginning that we found that it will go off, like not really fast, but like for example, the average system for this yellow line will deviates like this. It still ends up at the bottom, but it doesn't predict well, and it's not good enough to predict whether the swimmers will go back to the surface or not. And then we stuck there for a few days, and then we found that the problem is we overlook the initial condition. So before that, when we compare to trajectory, we use the exactly same initial condition, okay? Which means that this blue curve, this microswimmer here, it start at this position, okay? And for the average system, we also start with this depth, with this orientation. This is V, okay? And which is not the case. We averaged the original system, and then we also have to average the initial condition, so that for example, for this blue curve, and we start in the middle of it, so that this average trajectory will track these oscillations all the way, okay? And yeah, we basically just balance the uppercase x and lowercase x and z, large Z, small z, and large v, small v, at various order of epsilon, and find expression to do this correction for the initial condition, okay? And then we solve this problem. And further analysis, okay, so let's take a look back into the ODE system that we have, okay? So these two is decoupled from x, and we can see that here there exists a critical angle, phi crit, such that lambda plus cosine of 2 phi crit equals to 0. Okay? Which means that, so for example, you can see that I have some blue lines here, right? Which means the motion is confined within each blue boundaries. The microswimmer cannot go from here to here, which means that if your orientation phi is within this region at the beginning, that you will stay in this region forever. It cannot go through. It can never go through. Okay. And we solve this system, and yeah, the solution lambda will be 1/2 of the arc cosine of minus lambda. Okay, and because the arc cosine is defined in 0 to pi, right? So 1/2 of that is defined in 0 to 2 pi. Okay, and actually this equation have 4 solutions in total, which is lambda and pi minus lambda, pi plus lambda, and 2 pi minus lambda. And these four solutions lie in the 4 quadrants respectively, which means that this one is guaranteed to be in this first quadrants. And this one will be in the second quadrant for sure, and this one will be the third quadrant for sure, and this one will be in the fourth quadrant for sure. Okay. So next, of course, we want to solve this, right? Because we want to predict whether the microswimmer will swim back to the surface or not. Okay. So yeah, let's try to look deeper to the graph. We can see that there is a separatrix between the trajectories. So some swimmers, it can actually go from a position that is slightly above this red curve, okay, and go along with this red curve, very close to this red curve, but slightly above it, and it can go very, very, very deep, very, very, very deep, but it's still above the red curve, the red separatrix, okay, to somewhere that is very deep, and then jump back to the surface. Okay, actually it can go even deeper than this. It can go very deep to the minus, actually minus infinity. Okay, not infinity, but it can as deep as that. Okay, it can go to -10 or something like that, and then come back to the surface, and we call this a cusp of motion. Okay, and for positive lambda, which is the prolate swimmers, and the cusp is in the first region, in region 1. And for this oblate microswimmer, this cusp will be in the region 1, 2, 3. Yeah, in region 3. Okay, and here it's also the same. The microswimmer can go somewhere slightly above the right curve and go very, very, very deep, and then still manage to come back to the surface. Okay. Yeah, and because these trajectories, they are symmetric with respect to pi over 2 and 3 pi over 2, then we just guess. We just at the beginning that it's natural to guess that this separatrix curve will go through a point that is that has phi equals to pi over 2 and z equals to minus infinity, because it's symmetric, right? So this red curve should go through pi over 2 comma minus infinity. Okay, and this separatrix at the right hand side should go through this point, 3 pi over 2 and 0. Okay, and this is also the case. In this case, we have to reverse the criteria. Okay, so at the left hand side, then this separatrix curve has to go through pi over 2 and 0, and this one has to go through 3 pi over 2 and minus infinity. Okay, so yeah, and we find that it's actually solvable. We divide this equation by this equation. Okay, so dz over d phi will be this, and we do some substitution. We can actually, very surprisingly, that we can solve it. Okay, solve the bonding curve, and yeah, the expression looks something like this. This z naught z0 is the initial depth, and this v0 is the initial orientations of the microswimmer. Okay, so to solve it, actually it's a long expression, but we do some simplification. We define an operator delta x of x. So if x is 1, then delta 1 equals to tanh of 1 times these things, blah blah blah. Okay, and then now we have this expression. And we have to deal with the positive lambda and negative lambda case separately, because you see that they have different situations where for positive lambda we have cusp at the left, and for negative lambda we have cusp located on the right hand side. Okay, so basically that for positive lambda, then we're setting z equals to minus infinity with phi equals to pi over 2 in equation 25, which is this one, and we find the left hand side curve, a function for this left hand side curve, this one. Okay, and for this one we set z equals to 0 and phi equals to 3 pi over 2 to find this one, to find this right hand side separatrix curve. Okay, and for the negative lambda we do the same thing. So here we set z equals to 0 and phi equals to pi over 2 in equation 25, and find the function for this curve and also for this one. Okay, and then we successfully find the prediction curve that people can use to predict whether the microswimmer will swim back to the surface or not. Okay, so for example, if you start at this depth, then the swimmer with orientation within this region will end up at the bottom, because the gray area here means that the swimmer will finally end up at the bottom. Okay, it will at the bottom, and the white part is saying that this microswimmer can swim back to the surface at the end. Okay, and also for this, also here. So next, it's a natural question to ask. So for example, if we have tons of micro machines, these spherules micro machines, okay, and we grab a bunch of them, like we grab 10,000 of them and throw them into and release them at a certain depth. For example, I get 10,000 micro machines here, and we release that here. Okay, and how will that? How many of them? How many of those will swim back to the surface, and how many of those will end up at the bottom of the water tank? If the orientation of those microswimmers are distributed evenly. Okay, so it's basically just the fraction hidden surface will be this white part divided by this range, which is 2 pi. Okay, so the fraction hidden surface, we calculate that with this formula: 1 minus right hand side curve minus left hand side curve divided by 2 pi, because this part is actually fraction hidden bottom. So we use 1 minus that to find the fraction hidden surface. Okay, and this is the plot. And this is the plot. Okay, let me clean that a little bit. So you can see that the oblate microswimmers are more affected by the waves, because as it goes deeper, more microswimmer will not be able to swim back to the surface. Okay, and for prolate microswimmers, it's also affected by the wave, and with very depth, the fraction hidden surface will change, but not as large as the oblate microswimmers. And we found that there's 2 limits. Okay, so for lambda equals to 0 and lambda equals to 1, the fraction is always 0.5, no matter what the depth is, because for lambda equals to 0, it's a perfect sphere. Okay, the perfect sphere that, because it's symmetric in all directions, and then it's not affected by the fluid field. Okay, so if it goes in this direction, and it's going to end up at the bottom for sure. If it's going this direction, then it's going to swim back to the surface for sure. Okay, and for lambda equals to 1, those microswimmers are thin needles. And there are some very, very thin needles. Okay, and because too thin, then it's not going to be affected by the wave also. Okay, so similar to this one, if it's swimming this way, then it's going up. If it's swimming this way, then it's going down. Okay, and for lambda equals to -1, these are just some very, very thin plates. Just imagine this as a thin plate. Okay, this 3D thin plate. And swimming in this direction, and because it has a large contact surface, so it's kind of intuition that it will still be affected by the wave. Okay, and therefore it's not always 0.5 here. Okay, and if you look closely, that there's a trend. Okay, there's a trend. So when we make the initial depth deeper and deeper, then this curve will fall down. Okay, there exists a horizontal line in the middle, and this is not approximate straight. It's actually straight. It's literally a straight horizontal line located at depth z naught equals to minus log of square root of 2, and this is actually found by some calculations. It's not here. Yeah, it's here. So because the fraction hidden surface is calculated by this, so in the numerical simulations, we observe that there's a line like this, very, very flat, nearly flat, but we don't know whether there's exactly a flat one. Okay, so I go through the calculations, then you use this left-hand side, right-hand side curve to minus the left-hand side curve. This is some draft that I wrote months ago. Okay, and surprisingly, there actually is a solution that allow us to find this special depth, which means at this depth, if the swimmer start at this depth, then no matter what the shape is, then it's always going to be that 50% of the swimmer will go back to the surface, and 50% of the swimmer will go down to the bottom of the water tank or the water. Okay, so and of course you have to assume that a evenly distributed orientation for this bunch of microswimmers that you release at this depth. Okay, so it's actually it's not very complicated, but at the end you have a very clean answer, which is -1/2 log of 2, and that is the special depth, or the special depth, or the fear depth for all shapes of microswimmer. Okay. Yeah, and and there's one more interesting thing that I want to share with you. Is this plot. I didn't label much on this because we didn't use it in the paper, but basically the color here means time, how much time each curve used. How much time you use. Okay, so blue, actually, you should trim off this blue part. Okay, only reserve the middle part. This is the color version of these face portraits. Okay, so you can see that we have a yellow tunnel at the right hand side, which means that let me check the orientation. Yeah, if the microswimmer start at this position and can go very deep, very deep, and still manage to come back. So in polar, it's this, and in Cartesian coordinates, it's this trajectory, this cusp. Okay, this cusp, and this time scale is actually log of 10. This is actually log of 10. Okay, so you can see that this trajectory cost, not this, should be these trajectories cost much more time than any other trajectory. Okay, it's actually maybe 100 times more, or at least 10 times more. Okay, because these swimmers can go very deep, and adjust its orientation there, and because it's very deep, the water motion is relatively small. The water motion, the wave motion is kind of not very obvious, and it allows it to adjust its orientation, and then after it's ready, it swims back to surface. So you can see that there's a orange or yellow tunnel here. Okay, yellow tunnel here. So yeah, thank you for watching. I think that's all I want to share today, and yeah, my sincere apology that I cannot come to give a live talk. So at this moment, I am probably still in a traveling hall in some dark room playing with lasers, and try to finish my last 2 lab credits so that I can graduate. Okay. So everyone, keep warm and stay safe, and also my sincere congratulations to Dr. Yufeng. Yeah. So if you have any question, that you can ask me in Slack. My name is Kunli Ma. This man. Okay. And yeah, that's all. Thank you.